Here is an interesting puzzle from Mensa Mumbai and Mensa India's WhatsApp group for puzzles. And this puzzle, if you try to do it algebraically or trigonometrically, is going to prove extremely tedious and long-winded. But if you try to get it using a certain insight, then it becomes extremely simple and the solution is delightfully elegant. Although the solution is going to be short, this video that I'm posting is going to be longer than usual because this puzzle is very rich in what it has to offer. There are lots of interesting observations we can make. Based on that, we can get some very interesting and valuable insights. And based on that, we can even modify the story, spin another interesting story around this puzzle score. And finally, we'll be doing some kinematic analysis, like what is the kind of motion involved, speeds, velocities, that sort of thing. And then we'll also look at the generalization. So I have given this kind of index here, and you can go through this index and jump to any part if you want. But I would rather have you stay with us throughout this presentation and enjoy this video. Okay, so let's go down to the puzzle itself. This puzzle starts with a kind of ground, which is like a flat plane in geometry. And in that ground, there are these four walkways. We can even number them like 1, 2, 3, and 4 here. And these are like straight lines in that plane. And walking on these walkways are four walkers, say morning walkers there. What I've shown here are not necessarily their starting positions, nor is this any snapshot of their walk. They're just representative figures on this. The important part is that each walker is confined to his or her own straight line path, number one. Number two, they are doing so steadily at their own pace. And there is no turning back, there is no pacing back and forth, nothing. So they'll be all progressing in a straight line at a steady pace. And then the puzzle tells us that one morning, as these four people are walking on these paths, something extremely interesting happens. When walker number one reaches this point, walker number three also reaches that point. So they actually meet at that intersection. And then as walker number one proceeds, he meets walker number four, then he meets walker number two, and so on. Then walker number two also experienced something similar. When she reaches this point, she meets walker three, and then at the next intersection, she meets walker four. And we have already told you that she meets walker one, of course, here. Now the question remains is, would walkers number 3 and 4, whose paths intersect at this point, would be actually meeting there? That is, would they be reaching there simultaneously? And that is the question we have to answer in this puzzle. Okay, so that is the puzzle statement. If you want to pause the video here and try this puzzle on your own, go ahead and stop the video. Otherwise, we'll go ahead and look at the solution. Okay, so let's start by thinking about what is happening here. Well, there are four intersecting lines, four intersecting paths, but it is not just the intersection of lines that we are interested, but some moving objects reaching those intersection points simultaneously. So here, not only the space, not only the coordinates, okay, are important, but also the time instances at which something is happening. So to this, information of plane geometry, x and y axis or xy plane, we need to add the third parameter, and that is time. So let's add a time axis to this whole thing. And then we will be representing these walks not only in their spatial reference, say x and y coordinates or their position, but also in terms of their time coordinates, the instances at which they are at a particular position. If we do that, then we get a line like this. For example, this walker number one. He is proceeding along this line, and as he does so, the value of time, the time coordinate is increasing, time is passing. So this time coordinate, we can actually look at this in 3D. So it is actually a straight line, okay, like this, but we are plotting it in a 3D space. Okay, so as walker number one progresses on this path, time is flowing forward, and therefore his time coordinate is increasing. Now, similar kind of graph you can plot for walker number two as well, and it will look like this. And these two paths are going to intersect. Okay? Even without looking at it closely, we can be sure of that. And why so? Because we know that walkers number 2 and 1 meet at this point. That means they are not only having their spatial coordinates, x and y coordinates, the same, but also their temporal or time coordinates equal. So these two are intersecting at this point. And if there are two intersecting lines, we can definitely pass a plane through that. Okay? So let's mark that intersection here. And that intersection allows us, or tells us, that it is possible to pass a plane through that. So let's see what kind of plane is this. Okay, you can see this is a plane that is encompassing both these lines. Okay, let's call these lines as the time-space lines of walkers 1 and 2. Okay, on with the story. Walkers 1 and 2 are also meeting other walkers. For example, 1 is meeting walker number 3. Okay, so that particular intersection can be now projected on this line. Similarly, walker 2 is also meeting walker number 3, so that we have projected on this time-space plane. You can see those here. So walkers 3's walk, or 2 points on that walk, are now available. And it's a straight line walk, so we can actually connect them with a straight line. So this is the time-space representation of walker number 3's walk that morning. Okay. And because two of its points lie in this plane, the entire line is going to lie in that plane. Same thing we can do with walker 4. He meets walker 1 here, and he meets walker 2 here. So we can draw that line, and that is also going to lie in this plane because these 2 points lie in that plane. And why these 2 points lie in that plane? Because they are on these lines which are in the time space plane. Okay. So now we have 4 lines. Okay. The walk of, or the record of walker 1's walk, walker 2, walker 3, and walker 4. And these 2 lines, the time space records of walker 3 and 4, they are lying in the same plane, and they are not parallel lines, and therefore they must intersect. And what is the meaning of intersecting here? See, intersecting in the ground, that means just the paths are intersecting. But intersecting in this time-space plane means they are not only having the same x and y coordinates, the same position, but they are also having the same time position, so time coordinate. And therefore, they are going to meet there simultaneously. In simple words, they are going to actually meet. So that's the solution of the puzzle, that yes, walkers number 3 and 4 will indeed meet at the intersection of their paths. Okay. Now that we have solved this problem, let's make some interesting observations here and get some insights. For that, we are going to draw a plane here in the plane of the ground itself. So because of that, our time axis is going to be normal to that plane. And because it is normal, you can call this plane as t is equal to 0. Now, if you take this plane t is equal to 0 and if you move it upward, okay, what will happen? It will become t is equal to say 10 minutes or 5 minutes or something constant. Okay, so t is equal to constant plane. So as the time progresses, this plane would be kind of moving up and up like this. Okay, and all the time it will be, of course, intersecting our time space plane, this pink plane here. And two planes, as you know, always intersect in a straight line. So here is a straight line of their intersection. But along that straight line, something interesting is happening. Okay, let's zoom in and look at that here. So when this walker number 4 is at this point in space and time, then the time value, and when walker 3 reaches this point in space, his time value, and walker 2's time value when she reaches here, and time 1's walker time value when he reaches here, all those times are equal because they are lying on a plane t is equal to constant. But talking in terms of space, they are forming a straight line. So that is the trick of achieving this interesting coincidence, that if all the walkers want to meet some other walker, at every intersection. How they must walk? They must walk forming a straight line. Of course, there is a different and easier way of visualizing this all, and for that we are going to modify the story a bit. So that is coming in the next part. Now we are going to modify this story a little bit, and for that we'll be rotating this entire ground and we'll be making it sort of vertical so we can stick it on our wall kind of. And then we are going to imagine that this ground is actually a ship. These four walkways are not walkways, but they're actually pipes. And the four walkers are nothing but four mice. So here they are. So these four mice are going to run through this pipe. And if you ask me why, well, because the ship is sinking. Right now they are aligned along a straight line and water is rising in the ship like this, and therefore they are going to move so that they can keep just above the water. And see, as the water level progresses upward, the mice are moving in the pipe, and here the two mice are meeting, the first two at the intersection. Then as the water level rises, here is a second pair of mice, okay, meeting at this intersection. Then there's a third pair meeting. Then there's a fourth one, the fifth one. These were all intersections which were given to us, and this is the one we were interested in finding out whether the two walkers or these two mice meet or not, and they indeed meet at this point. So this is a simpler solution to this problem, that you take the entire ground, okay, and just make it vertical, put it in a vertical plane, and then you imagine a horizontal line like this water level here, which is steadily rising up, and that would make all the four walkers to move steadily at their own pace. So each one will have a different speed here, and they will be meeting at every intersection. And that brings us to the last part, the kinematics, or the analysis of this motion involved. So let's get rid of this spark here. Instead of these pipes, let us just consider their center lines. So here they are. And we don't need the water or even the mice here. Instead, we'll be using some points representing the four mice, and then we'll study their motion. So the motion is going to occur something like this here. As you can see, as the 4 points are moving along the lines, they are keeping along a straight line. They're always, lying on a straight line, and that straight line is progressing in the upward direction. So that's a trick of achieving this, and that's a trick that also ensures that points number 3 and 4 are going to meet at this point. Okay. Now let us analyze their velocities. Now, as far as these mice are concerned, for each one, there is no difference in the pace at which water is rising. So these are the velocities, water velocities, same for everyone. Let's call it VW. And then to keep within the pipe, the mice will have to move horizontally as well. So here are their horizontal velocity components. So this mouse here would be moving horizontally at this speed. This will be moving at this speed here and here. Okay, and the resultant of these two velocities, okay, the vertical velocity of water above which the mice are trying to keep, and their individual horizontal velocity components, they get added to the resultant velocity, which will naturally lie along the pipes themselves. And you can see, depending on the inclination of the pipe, the magnitude of velocity, the speed with which they are moving, is different. Okay, this pipe is inclined very gradually, and therefore this mouse will have to run along very fast, while these are close to vertical. So these mice don't have to run that fast. Okay, these two. So let's actually calculate this velocity component. So for that, we'll consider the inclination of these pipes, say angle alpha, beta, gamma, and delta with the horizontal. And then this angle alpha is subtended here as well. We know the opposite side, that is velocity of water, VW, and we want to find the hypotenuse. So it's going to be opposite side and hypotenuse. So just divide by sine theta or multiply by cosine theta. So the actual expressions for velocities are V1, okay, will be equal to VW, velocity of water, into cosine of alpha. Here it is multiplied by cosine beta, gamma, and delta. Okay, so the velocities are proportional to the cosine of angle of inclination. Okay, that's a kinematic conclusion that we get. So this was a problem which was very fertile in the insights and observations we could make, and quite a bit of learning we could derive from this. Thank you for watching.